So other method of solving first order differential equation is the transformation of homogeneous. And when we say before you can use or you can apply transformation of homogeneous to solve any differential equation, first your differential equation must be homogeneous. Your differential equation must be homogeneous. And for your differential equation to be homogeneous, individual equations must be what? Homogeneous function. So first, before you use transformation of homogeneous differential equation, first we'll talk about homogeneous function and homogeneous differential equation. So first, I'll talk about homogeneous function. So you say you define a function, my f of x is a shortcut of function. So my function, let's say f of x, y is said to be homogeneous function. So my function f of x, y is said to be homogeneous function if there is, let me speak mathematical thing. If there is a certain scalar, let's say lambda is, let's say open the bracket, scalar, such that when I multiply my individual x and y by the scalar plus lambda x, lambda y, I'll get a certain lambda out, taking the power of n, my function f of x, y. All this n is any natural number. So anytime I multiply, this is my function already, but anytime I multiply my function by a certain scalar, that's, let's say, lambda x, lambda y, at the end of the summation, I have to factor out, the final answer I'll get, I can even factor a certain scalar out, taking the exponent of any number, the function. So that's termed as homogeneous function. So let's solve two examples of this type of equation and let's see. So we have 3 questions here to show whether the following is what homogeneous. We have alpha, beta, gamma. So first, we'll solve our alpha. So alpha, I have my f of x, y is equal to x taken the power of 4 minus x taken the power of 2, y. A function is said to be homogeneous if I multiply my x here by lambda, multiply my y here by lambda, and then I'm able to factor a certain lambda taking the power of n. This n is a degree, the function. So now let's come back to our alpha here. So here, the first thing we have to know here is that I have to change this x towards lambda x, change this y towards lambda y. So I'll have my f of lambda x, lambda y to be equal to, so whenever I see x, I change the x towards lambda x. Whenever I see y, I change the y towards lambda y. Then I'll have for my x taking the power of 4 lambda x taking the power of 4 minus lambda x taking the power of 3 lambda y. This one is the same as lambda taking the power of 4, x taking the power of 4, lambda taking the power of 3, x taking the power of 3, lambda y. Lambda, so we have lambda here taking the power of 1, so lambda to this one, my lambda taking the power of 4, x taking the power of 4, minus lambda taking the power of 4, x taking the power of 3, y. So we're writing this one. I have my f of lambda x, lambda y to be equal to. Now I can see that lambda taking the power of 4 is common within both sizes. This, we have lambda taking the power of 4, here we have lambda taking the power of 4. So I'll factor those lambda taking the power of 4 out. Then I'll have lambda taking the power of 4 out. What is left here is my x taking the power of 4 minus x taking the power of 3, y. But you can see from the question that my f of xy was x taking the power of 4 minus x taking the power of 3, y. So then this is my what? F of x. So therefore, I'll have my lambda taking the power of 4, my f of what? X, y. So therefore, my f of lambda x, lambda y is equal to what? Lambda taking the power of 4, f of x, y. So the degree here, my n here is what? 4 for the first. So we just conclude that hence f of x, y is homogeneous. So for the second one, beta, we have m of x, y is equal to x taking up x squared minus y squared all over 2x y plus what y squared. Therefore, my m of, so we are changing the x and the y. So we change this x to lambda x, y to lambda. So I have lambda x, lambda y to be equal to lambda squared x squared minus y squared lambda squared all over 2 lambda squared x y plus lambda squared y squared. Lambda is common, so I'll factor the lambda, so I'll have lambda squared out in numerator x squared y squared, and the denominator will have lambda squared out 2xy plus what y squared. Yeah, I can do. Yeah, don't take this one to cancel this one. Otherwise, you will not fulfill the real definition of homogeneous function. So what we have to do here is that I will rather move this lambda squared to this side. Then I'll have my m of lambda x, lambda y to be equal to lambda. This is taking the power of 2. So this one will come minus 2 here. Then I'll have my x squared minus y squared all over 2xy plus y squared. Here, my m of lambda x, lambda y will be equal to lambda 2 minus 2 is what? 0. My x squared minus y squared all over 2xy plus y squared. So you can see that this side represents or resemble the function. That's my m of x. So therefore I'll have my m of lambda x, lambda y to be equal to lambda taking the power of 0, my m of what? X, y. So you can see that this one too is homogeneous function with a degree of what? 0. So hence m of x, y is homogeneous function with degree of 0. We have f of xy is equal to x squared plus y all over xy. So here to change our x and our y to what? Lambda x, lambda y respectively. So I have my f of lambda x, lambda y to be equal to lambda x all squared plus what? Lambda y is plus all over lambda x multiplied by lambda y. So here we will have my f of lambda x, lambda y to be equal to lambda squared x squared, that's this side, plus lambda y all over my lambda squared x y. And for the numerator, I think lambda is common in both sides, so I'll rather factor lambda out. So I have this lambda squared, so I'll have lambda x here plus y here all over lambda squared my x y. So this one will be something like lambda 1 minus 2 lambda x plus y all over x y. This to this will have lambda negative 1 lambda x plus y all over x y. So I'll have my f of lambda x, lambda y. But watch it. You see here we have lambda taking the power of negative 1. This, but this one it doesn't it's not the same as my f of x. All because there's a lambda here. If you go back to our original question, there's nothing here. There's no lambda here. So that means that this, when I multiply my x, when I multiply my x and y by lambda, I will not get a reduction. So therefore, hence, so listen, we have therefore my f of lambda x, lambda y is not equal to lambda taking the power of, let's say, in f of x of y. So hence it is not homogeneous function. So in conclusion, when we say a function is said to be homogeneous, when we multiply our function by a certain scalar, at the end of the solution, at the end of the problem, we will be able to factor a certain scalar out. Then at the end of the problem, we will factor a certain scalar out, multiply by the original quotient. So when you try and maybe at the end, you are still having a lambda in the function. The function is called homogeneous function. So that's it. Thank you. Now we have done something about homogeneous function. So the next thing is homogeneous differential equation. And so let's take that one. So we have, so I'll clean this one now. So we have homogeneous differential equation. And for homogeneous differential equation is of the form my m of x y dx plus n of x y dy is equal to 0. The trick here is that we will have something dx plus something dy here. So let's say we have something dx, something dy. So the one multiplied by dx will be your m of xy. The one multiplied by dy will be your n of what? Xy. And here, for you to show that a given problem is homogeneous differential equation. First, this one must be homogeneous function. This one too must be homogeneous function. Then compare the two cases. If their degrees are the same, then you can say that yes, indeed, this differential equation is what? Homogeneous differential equation. So now let's try to solve two or more three questions. Let's see whether everything will be okay. Thank you. So now we have this question. Show whether the following differential equation is homogeneous. You have alpha, beta, and gamma. So first, we solve the alpha. So we have alpha here, x squared plus y squared x minus x squared minus y squared dy is equal to 0. But let's compare this one to the original form. You know the original form, we have m of xy x plus n of x y dy is equal to 0. So I can see that this, but before we use it, this one isn't the same as this one. No, because no here we have it plus, but here we have it with negative. Then I have to change this one to plus. Changing this one to plus, now I can multiply this one through by whatever it is. So I'll have something, or this one will change to my x squared plus y squared dx plus y squared minus x squared dy is equal to 0. So from here I can see that my m of x y will be for the beta we have x squared y dx is equal to y squared. But you should bear in mind that let's compare this one to the original form. The original form is a certain m of xy dx plus a certain of what n xy dy is equal to 0. But looking at this particular problem, we have to rewrite this one. We have to rewrite in terms of what n of xy and also. So this one, rewriting this one, we'll have x squared dy is equal to y squared dx. So it's not the same form of this one. It's rather something dx plus something dy is equal to 0. Then I have to move this one to this side. Then I'll have my y squared dx minus x squared dy is equal to 0. Yes, so the original form we have something dx plus something dy is equal to 0. So I have to change this negative to a positive. Then I'll have y squared dx plus negative x squared dy is equal to 0. Then from here I can say that my m of x y will be equal to y squared plus my n of x y will be equal to negative x squared. So case 1, taking my m of x y will be equal to, so now I'll change this x just like what we did in the first example. I'll have m of lambda x lambda y to be equal to, even here there's no x, so we'll just have lambda squared y squared in which this one is the same as lambda squared and function m of what? xy. So that's for the case 1. For the case 2, we'll have my n of xy to be equal to negative x squared, and changing this one to, so we have lambda y to be equal to lambda x squared, lambda squared x squared. This one is the same as lambda out negative x squared. This one too is the same as lambda squared by n of what? x1. So comparing the two cases, from case 1 we have the degree to be 2, and from the case 2 we have the degree to be 2. So you can see from both cases that the degrees are the same. If the degrees are the same, then we consider the differential equation is a homogeneous differential equation. So hence the differential equation is what? Homogeneous. Since the degrees in both cases are the same. So that's it. So here, because we have the degree of this of the case 1 was 2, and the degree of case 2 was 2, you can say that the differential equation is homogeneous. So now we have the last example we have to try and see. So in conclusion, they will give you differential equation, and the thing you have to know here is that try to compare to the original form. That's your m of x y dx plus your n of x y dy is equal to 0. Always you have to get that form. Know your m of x y. Know your n of what? X y. Take your m of x y. Check whether it's homogeneous function with a certain degree. Take your n of x y. That one to check whether it's homogeneous function with a certain degree, and then compare the two cases. If the degrees are the same, you can say that yes, hence the differential equation is a homogeneous differential equation. If the degrees, maybe we'll get a particular question in which the function will be differential equation, the function will be homogeneous, and maybe the two cases too. If you compare the degrees might not be the same. So the trick here is that if the degrees are the same, then you can say that the differential equation is homogeneous. If the degrees are not the same, it's not homogeneous differential equation. And even if one of the cases requires no homogeneous function, then you can say that it's not homogeneous differential equation. So that's it. Thank you.